what we're doing. Again, as I go through, remember, my numbers are going to be different than yours, but the process is going to look pretty similar. So if we look at problem number 3, you're going to be launching what looks like a rock from the edge of the top of a building. So it looks a little bit like this. We have our building here. We're taking our rock and we're launching it up at a certain angle. And we're told that that rock is going to fall downward. As we know things tend to do in projectile motion, it will be launched up, then eventually come back down. And we're told the rock lands a certain distance away from where it begins. Now in my problem, I'm given a distance of 18.5 meters. That's how far our rock lands from where it began. 18.5 meters. Now I'm also given a little bit of information about my kind of initial conditions, my launch velocity is what we've been referring to it as. I'm told here that I'm launching with an initial velocity of 12.6 meters per second at an angle of 60 degrees. It's probably not the scale, but we can get the idea here. I'm launching at some angle above the horizontal. So what we're asked to solve for here, let's look at our problem statement. It says this. How tall is the building? Assume the ground is level and that the side of the building is vertical. So we're assuming the ground is level, the side of our building is directly vertical. The acceleration of gravity is 9.8 meters per second squared. I know we've been using negative 9.81. Here, Quest wants us to use negative 9.8. The reason that's important is because when we plug values in, we need to make sure that we're within a good range of what's appropriate. So what we're looking for here is really this value, the height of our building, which if we were to give that a variable, we would call that delta y. That's what we're trying to solve for here. So just like with any projectile motion problem, the first thing we're going to do is start by listing out our variables. So I'm going to come to a clean page, and we'll come back to this to refer to. So in the x direction, I'll list out my variables delta x, initial velocity in the x, final velocity in the x, acceleration, and time. And I'm going to do the same now for the y direction. Delta y, which is what we're ultimately going to be trying to solve for, initial velocity in the y, final velocity in the y, acceleration in the y, and time. Now before we start to go and fill in any of the values we're given here, we know we can always start with our acceleration values. In the x direction, we're going to assume that the acceleration is 0. Nothing's going to cause our object to speed up or slow down horizontally. We're going to kind of neglect air resistance. And in the y direction, we're going to use negative 9.8 meters per second squared. If you use negative 9.81, it should be just fine, but we're going to go ahead and use this because it's what Quest wants us to use. Now, if I look back at my picture, I'm given a few numbers here. I'm told that my object travels a horizontal distance of 18.5 meters. So I'm going to go ahead and plug that in to my delta x. That's my range, if you will. My horizontal distance, 18.5 meters. Now, I'm looking for here my delta y. How tall is our building? Okay, kind of how high are we launching this projectile from? Now, if we come back to our original picture, we're given a velocity of 12.6 meters per second at an angle of 60 degrees. Now, it's going to be your tendency to want to take that value, 12.6, and just plug it in to either the x or the y direction. But what we have to remember is that that velocity, 12.6, is neither in the x nor in the y. It's kind of in both directions. So we're going to treat that velocity as a vector and break it down. So I'm going to come to a clean page, and I'm going to redraw my velocity vector. We're launching with a velocity of 12.6 meters per second at an angle, of 60 degrees. So what I'm going to try to do is I'm going to try to break this velocity vector down into some vector in the x direction and some vector in the y direction. Remember, when we're dealing with vectors, okay, especially when we're dealing with a velocity vector in projectile motion, some of our velocity is horizontal and some of it's vertical. And for us to really be able to analyze this problem, we need to know what's going on just vertically and just horizontally. So I remember my acronym for trig functions, which was SOHCAHTOA, I can use my given angle and my hypotenuse, my overall velocity vector, to find out those components, the x and the y component. So if I look at my x component, that's going to be adjacent to my angle, and I have my hypotenuse. So that means I'm going to use my cosine function. So what I'll do here is I'm going to write out cosine of my angle theta, which we know is 60 degrees, is equal to my adjacent side, which is v naught in the x, over my hypotenuse, 12.6 meters per second. Once I'm here, if I want to get that initial velocity in the x direction by itself, I'm just going to multiply by 12.6. On the right-hand side, that will cancel out that value of 12.6, and then we'll move it over to the left. So I'll be left with an expression that looks like this. V naught in the x direction is equal to 12.6 cosine 60. So 12.6 cosine 60, if I just momentarily plug that into my calculator, make sure we're in degree mode, not radian, I'll get an initial velocity in the x direction of 6.3 meters per second. And so I'm going to take that and immediately place it back into my list of variables. 6.3 meters per second. And it's really helpful for me to always take those values and relist them out. Now I know that in the x direction, my velocity is going to be constant because I have no acceleration. It's not changing at all. So my final velocity is also going to be 6.3 meters per second. Now, even though we're going to be tempted to try and take these values in the x direction, start solving for maybe time, make sure we go through and find that other vector because we will need it later. So if I come back to my vector, now I want to find my y component. So my y component is going to be adjacent to my angle, and I have my hypotenuse here. So I'm going to use my sine function. If you've noticed, since we have this adjacent side, and I have my hypotenuse, or excuse me, I have my adjacent side, I want to find my opposite. I could go through and use tangent if I wanted to, but if we don't solve that first, then we'll need to use the sine function to find that velocity in the y direction. So I'll write out my expression to find velocity in the y. Here, not cosine, but sine 60 degrees is equal to my v naught in the y divided by my hypotenuse. That is adjacent over hypotenuse. Excuse me, opposite over hypotenuse for our sine function. So, just like I did previously, if I want to get v naught in the y by itself, I'll multiply by 12.6 on both sides of my equation to move that over. What that will leave me with is an expression that looks like this. My initial velocity in the y direction, v naught in the y, is 12.6 sine of 60 degrees. So if I plug that into my calculator, 12.6 sine 60, again make sure we're in degree mode here, not radian, I'll get 10.91 meters per second. So now I have both of my components of velocity. I'm going to come back to my list of variables and plug this in. So 10.91 meters per second. And just to make sure, come back here, come down, 10.91 meters per second. I might have said 12 there, I apologize. Should be 10.91 meters per second. So, looks like I have a pretty good amount of information here. You'll notice what's still missing is my time variable. And I'm going to need that time variable to eventually find out how tall my building is. So, what we're going to do is we're going to use what we know in the x direction to find time, plug that in, and use my time to eventually find my height. So, if I look at my kinematic equation sheet, looks like I have a lot of variables here. But if you remember, one of the simplest equations to use for the x direction is equation number 2. So we're going to go there. Equation number 2 looks like this. Delta x is equal to initial velocity in the x direction times time plus 1/2 acceleration in the x t squared. Now, one thing that's nice here is that I know my acceleration in the x direction is going to be 0. So, this entire quantity is going to go to 0 because I know acceleration in the x is 0, so all of that's really going to be erased from our equation in this scenario. That's going to leave me with a much more simplified equation. Delta x is equal to initial velocity in the x times time. So here I'm just going to plug in what I know and solve for time. I know my delta x is 18.5 meters. I know my initial velocity in the x direction was, I believe, 6.3. Let's double check, yes. Meters per second. And then I'll multiply by time. So once I've plugged in my variables to this equation, I need to solve for time, meaning I'm probably just going to divide by 6.3. We'll do that on both sides of our equation, divided by 6.3 meters per second. Doing so is going to cancel out this value of 6.3 on the right-hand side of my equation to leave t by itself, which we were looking for. And now, in order to solve for my time, I'm just going to plug in 18.5 divided by 6.3. So in doing so, what that's going to give me is a time value of about 2.94, roughly, if I round up here, seconds. Now again, this isn't our final answer. One thing we've talked a lot about with projectile motion is that we're not always going to have to go through one step to get to our final answer. Sometimes it might take us 2 or 3 steps in order to get there. You'll notice in your problem statement, it doesn't tell you anywhere, solve for time. But it's important for us to recognize we're going to need time very often in order to find some of the other things we're asked to solve for. So I'm going to come up, I'm going to put that time into my list of variables, 2.94 seconds in the x and 2.94 seconds in the y. Okay? So now that I have my time, I want to solve for delta y. So if v1 is not a factor, we're not really concerned with our final velocity here. If I look at my kinematic equation sheet, that tells me I'm probably going to use equation 2. So now let's list out equation 2. Looks like this. Delta y is equal to initial velocity in the y times time plus 1/2 acceleration in the y times t squared. One of the nice things here about using equation 2 is that our variable we're looking for, delta y, is already by itself. So I don't need to do any work to get delta y alone. All I'll need to do here is plug in everything else I've already solved for. So delta y will be equal to my initial velocity in the y, which if I refer back to my list of variables was 10.91 meters per second, times my time of 2.94 seconds. Then I'm going to add in 1/2 a in the y, so plus 1/2 my acceleration in the y. Remember, we're going to use 9.8 meters per second squared times 2.94 squared. Kind of ran out of room there, sorry about that. But we can see all we're doing now is just plugging in all of our values. So I'm going to take my first value, 10.91 times 2.94, and my equation will look like this. Delta y, is equal to, this value here would be about 32.0754. It's a lot of numbers here, but I'm going to go ahead and write them all out and not round until the end, just so I make sure my final answer is within a pretty good range here. Then I'm going to add that to these values over here. I'll take 1/2 times negative 9.8 times 2.94 squared. Don't forget to square that time value at the very end. When I do that, that's going to give me a value of about negative 42 point, looks like about 354. Okay, you notice I've kind of left the units up here because I've already made sure I plugged everything in SI units, meters and seconds. So my final answer should be in meters like we're looking for. Now, if I just combine these two terms, 32.0754 and negative 42.354, we'll see what we get. And it's going to leave me with a value that looks negative. And mine says negative 10.28 meters. Now this is a little bit tricky. Okay, the tricky part here is that we assumed our acceleration in the y was negative. And on the problem statement you're given in Quest, you're told to use a positive value, but I want us to make sure we're using negative. Okay? All this negative here means is that my object was traveling in the negative direction, negative 10.28. But when you plug in your answer on Quest, make sure you plug in a positive value. Because we're not really looking for what was the object's displacement. We're trying to find the height of the building. And even though our height of the building is going to be the same value, it's going to be a positive value. We're going to say that building is positive 10.28 meters because that's really the opposite sign of what we